Welcome to the Horizon Coordinate System module. In this module, you'll become familiar with the Horizon Coordinate System and be introduced to the basic elements of the time evolution of the celestial sphere. To prepare for this module, you should already have viewed the Celestial Sphere module and the Introduction to Stellarium module. Let's begin. We begin with a display similar to the Introduction to Stellarium module, right? We're situated here in New Orleans and using a horizon image from the moon. Just trying to see if you were awake at the beginning. Using techniques we learned from the Introduction to Stellarium module, we're going to rapidly reset our location from New Orleans to Denver, Colorado in the USA. Clicking on left menu, top icon, location window, typing in Denver, finding Denver in the database, clicking on it, exiting. We're going to make sure that from the date and time window, we're on November 25th, 2021 as before, Thanksgiving Day in the USA, and we're going to start at about 7:30 a.m. This is a little earlier than the previous module, but there's a reason for that. Then we're going to use the sky and viewing options. In the first case, we have a perspective projection, which gives a flat horizon but causes visualization challenges later on. So you know I'm going to go for the Hammer Atoff for two cool reasons. I've also slid the brightness bar for the stars to the right, meaning effectively that we're going to get more star labels on our display when we call for them. Then we're going to move to markings. What on the celestial sphere do we want displayed? Well, we have the hotkeys that are helpful, but we need to turn on the celestial poles and zenith and nadir using this checkbox system. We're then going to click on landscape. We're going to change the horizon from moon to the zero horizon, our friend, which is very helpful for pedagogical reasons. That should be sufficient. So we close the box and we have again a curved horizon, but in fact the horizon is not nearly so vibrant green as before. Why is that? It's because it's pretty early on in the morning in Denver and the sun is just getting up. Now we're going to turn on the cardinal points. Recall we could obtain these by simply typing lowercase q, but let's start using the bottom menu, which is very helpful. And here we have the cardinal points icon here. We click on it once, and south, north, east, west, as well as intermediate points are listed on the horizon. Then we're going to, in fact, click on the compass marks. So effectively, this gives the azimuth, the angle from north through east along the horizon. Again, 0 degrees north, 180 south, and 360 or 0 back to north again. So let's just check that our azimuth is working properly. Let's face east, which should have an azimuth of 90 degrees, capital E. Recall faces us due east, 90 degrees. And what about due west, capital W, 270. Let's just see north again, capital N, 0 degrees. And again, we work in the principal domain, or at least we prefer to work in the principal domain in astronomy between 0 and 360 degrees. So let's face south again. We're now going to use the bottom menu to turn on the azimuthal or azimuth-altitude grid. Now, lines of constant azimuth are in fact these curved sort of vertical lines here. Lines of constant altitude are these roughly horizontal lines, lines parallel to the horizon. Lines of constant azimuth, also called verticals, are arcs of great circles, whereas the lines of constant altitude are small circles. So here we have, by definition, the horizon, lowercase h. It's time to highlight that as 0 degrees, altitude of 10, 20, 30, 40, 50, 60, 70. Let's go to zenith to make sure that zenith is 90 degrees altitude, a couple of up arrows, and we see the 80 degrees, and finally 90 degrees, capital Z or Z, zenith. So let's proceed back down to a more realistic perspective. Now let's turn on the meridian, the observer's meridian or the celestial meridian, semicolon. Now let's turn on the stars and their labels. We turn on the stars, lowercase s, if you'll recall, and Alt S for their labels. As I noted earlier, I've purposely decreased the brightness limit so that more star labels will appear. This will be very helpful as we monitor motions in the celestial sphere. Now let's head down to the bottom menu to the very right, and we see the rightmost icon is the quit icon. So avoid that. We're interested in this 4 icon bar right here, which governs the temporal evolution of the celestial sphere. The leftmost double arrow controls going backwards in time. The rightmost double arrow controls going forwards in time. The second icon from the left either pauses, or if I click it once, plays the actual rotation or revolution of the celestial sphere about the observer. So let's stop that, pause it. You have to see the icon pause to be paused. And then the third icon here is to reset the celestial sphere to the moment's time in your device, so your computer or clock time of your computer current time. So we're going to press the pause button, which really sets the celestial sphere into motion. Why do we not see much happening? Well, this is a real-time motion, and it would take a few minutes or maybe a good part of an hour to effectively notice that things are changing, moving from east to west. Now I'm going to click on the double arrow right, which means the celestial sphere is going to move forward in time. Stars are going to rise in the east and set in the west. I click it once, and you still barely see something happen if you really focus. Double click, and you see now you can perceptibly see stars and their labels moving. And if I click on again, it's even faster. And I could click again and again, and it becomes super fast. I'm going to stop it, and I'm going to move backwards in time. Double click, triple click, and I want to stop it right about here. Okay, so I've frozen the celestial sphere. Now I want you to focus on the star Antares, the brightest star in the constellation Scorpius, which will rise very shortly. So I'm going to click on 3 times, and I'm going to watch there Antares rising in the sky, rising over the eastern horizon. I'm going to slow it down now, and I'm going to ask you, when will Antares reach its maximum altitude? Rising means, by definition, it has an altitude momentarily of 0 degrees. Setting, the same thing. When will it achieve its maximum altitude, its maximum elevation from the horizon? So I think you see at each moment Antares in the eastern part of the sky, it in fact, azimuth is increasing and its altitude is increasing. I'm going to speed it up just a little, and I'm going to try to stop it very close to the meridian. Very, very close indeed. And it's going now at a real-time speed, so we won't see much motion, but I think your guess was correct, that in fact the maximum altitude a celestial object reaches is when it intersects the horizon. We call that a transit, when an object reaches the observer's celestial meridian. So an object, in fact, reaches its highest altitude when it's on the meridian, when it transits. What I'm going to do is try to get, see how good my reflexes are, try to get Antares as close to the meridian as possible. Whoops, went past it. Go back a little bit. Let's see if we can go back a little bit and try to get Antares. You'll see I have a method in my madness. Let's stop it right about here. Okay, so the pause sign's on, meaning that the time is not advancing, neither forward nor backward. Okay, now what I'm going to do is left click on Antares. So hover my mouse right on Antares and left click, and the database for each of the stars that you see is presented on the screen. So first of all, we confirm that we do have the star Antares, the brightest star in the constellation Scorpius, and a whole host of information about that star. Now we're interested in the transit and rise and set times. So you'll see here these three pieces of information. The transit time, when did it reach the observer's meridian? Local time 12 hours 11 minutes, 12:11, and see we've in fact very close, 12:10:55, which among friends is 12:11. In the same way, we see that the rise time of Antares, meaning that it rose from the perspective of Denver, if you had a perfect horizon, would be 7:48, and it would set at 16:34. There are a variety of other pieces of information, some of which you'll learn in your introductory astronomy course, some of which is information for upper year courses. What I'd like to do now is also point to one last piece of information, the azimuth and altitude of Antares at this moment. And you see that, in fact, its azimuth is 180 degrees, so I did really well. And its altitude is just over 23, almost 24 degrees. So that's its highest elevation. What I'm going to try to do now is to try to sort of brag a bit and see whether I can freeze it on the horizon. And we're going to look again to see whether our set time is accurate in this piece of information here. So what I'm going to do is run the clock forward again and see with my thumb on the play and pause button, see if I can freeze it just on the horizon. I'm not sure how close we'll get, but notice again, azimuth increasing, but altitude now in the west decreasing. Well, I'm pretty close. Let's see if I can fine tune it right about there. Okay, it's right probably on the perfect horizon, and it seems to be 16:33 here. I'm going to freeze the sky, and 16:32 here. Okay, so pretty good. Within a minute, my reflexes, not bad. Okay, so you can do that and explore all these stars, your favorite stars, as you see fit. Now let's remove the information on the screen, and remember we do that with the right mouse click. The horizon currently is opaque. I'm going to make it transparent by typing lowercase g. Notice there are some labeled stars below the horizon on our display. I'm going to raise the horizon a little bit so we can see the altitudes, negative altitudes. I'm going to raise the horizon a little so you can see stars with negative altitudes a little better. There's one star here called Hadar, which is the second brightest star in the constellation Centaurus. It's actually a double star. We're going to run time backwards, and I want you to guess whether Hadar ever rises from Denver's perspective. Does it ever appear above Denver's horizon? So you probably have a good guess, but let's see how this really works. So I'm going to click on it a few times, and we see that here's Hadar getting to closer and closer to the horizon. Is it going to make it above the horizon ever? Normally, of course, the horizon is opaque and you wouldn't be able to see it, but with the wonders of stellarium software, we can see this. And Hadar, it clearly isn't going to make it above the horizon. Its closest point was when it transited right here. Okay, so Hadar will never rise above the horizon. Stars like Hadar, stars which never appear above the observer's horizon, are called never-rise stars. It's a clumsy name, and I hope you can come up with something a little better than that. Now I'm going to lower the horizon a little bit from where we had it originally, and I'm going to face north. Again, capital uppercase N. Now what I'm going to do is run the celestial sphere forward in time using a few clicks. And I want you to look at stars like Capella, Castor, Deneb, Vega, and look at their behavior. Here's the horizon. Do they rise in the east and set in the west? So here's Vega. Here's Castor and Pollux. Oh, they're certainly setting. And we have these stars rising. Here's Capella, a very famous and bright star. It is set. It'll rise shortly. Okay, what about this star Mizar? A fairly bright star in Ursa Major, the Great Bear. Will it set? It's currently above the horizon. Will it ever go below the horizon? So follow Mizar very carefully. And in fact, it transits within maybe 4 degrees above the horizon, but does never go below the observer's horizon from Denver. So Mizar and stars like Mizar are always above the horizon. They neither rise nor set, but are always above the horizon, and they're called circumpolar stars. Perhaps you've seen the amazing time-lapse pictures taken from Mauna Kea or other sites in the southern hemisphere which show these amazing circles that stars trace out about the north or south celestial poles depending on your hemisphere. So at this point, it's helpful to try some thought experiments of your own based on these experiences with stellarium. For example, if you're at the equator, what are the circumpolar stars? What are the never-rise stars? What stars rise and set? And ask the same questions from either the perspective of the north or south poles. A few last items. What's the altitude of the north celestial pole from Denver? Okay, well, I'm going to turn off the star labels, Alt-S, so that Polaris doesn't occult the NCP symbol here, North Celestial Pole. And in fact, it appears to be the North Celestial Pole 10, 20, 30, just about 40 degrees altitude. In fact, the altitude of the North Celestial Pole is always the observer's latitude. And this, by the way, is one of the reasons why sundials work. Now let's face south, capital S, and turn on the celestial equator using the period. You see that the celestial equator intersects the meridian, the upper meridian at least right here. What's the altitude of that intersection point? Well, it's 10, 20, 30, 40, almost 50. And in fact, as you can probably guess, it's 90 minus the observer's latitude. Finally, we have noticed that stars constantly change their azimuth and altitude with time from a particular location, and that azimuth and altitude of a given star at a given moment will be different from different locations on Earth. Well, that makes sense because we all have different zeniths, amongst other things. Now, very large telescopes today, telescopes since the 90s, do use the azimuth-altitude or altitude-azimuth coordinate system, the horizon coordinate system, to identify and track stars. But it would be very helpful if there were a universal coordinate system that all observers could agree upon, independent of their location. That's the subject of the final module on the equatorial coordinate system. This concludes the module on the horizon coordinate system, or azimuth-altitude or altitude-azimuth coordinate system.